My name is Vahid Hasannaeimi. I'm currently a postdoc associate at the University of North Texas, working with Dr. Sandeep Mukherjee in the Department of Materials Science and Engineering. I did my doctoral studies here at the UNT. I started on 2015, and last year I joined Dr. Mukherjee as the postdoc associate. And I'm currently working on several parallel projects like materials development, materials that are resistant to corrosion, and coatings and nanocomposites. I also work on surface degradation of materials and development of functional and structural coatings. I work with Dr. Mukherjee. He is the associate professor in the Department of Material Science and Engineering, where he has worked on alloys development, metallic glasses development, and electrochemistry of these materials, like the mechanical performance of the material under low temperature and high temperature conditions. And more recently, he has also started some works on the electrocatalytic applications of the materials and like electrocatalyst development for energy storage and renewable energy industry. About the semiconductor invention that we filed the patent, typically copper in the crystalline form is widely used as the state-of-the-art interconnect material in consumer electronics, like integrated circuit. We call them ICs. The copper is used for dissipating the generated heat from these electronic circuits and components. But with the rapid trends in the lowering the dimension of these ICs and other electrical components, copper performance encounters with serious concerns, as its electrical resistivity drastically increased due to the nature of the crystalline microstructure. So once we have a crystalline structure, you have some inherent imperfection in the microstructure, like grain boundaries, like elemental segregation. All of these somehow prevent the electrons from passing through very quickly, and they increase the resistance. So on the other hand, the use of copper in nanoscale may also raise some other concerns, such as electromigration that affect the durability and reliability of these electronic devices. So this is the main problem for the current technology in this industry. To address the concerns that's raised by using the pure elemental copper in the crystalline form as interconnect, we proposed an alternative material, which is the binary silver copper alloy, but in the amorphous state. So by amorphous state, I mean that the alloy doesn't have the ordered crystalline structure. It has a disordered random distribution of atoms, and this gives excellent properties like mechanical, chemical stability, magnetic properties to the amorphous material. So silver has a high conductivity, and when it's alloyed with copper, they can both participate in electron and heat transfer. So we also propose to, as I mentioned, to use fully amorphous copper-silver alloys instead of a crystalline alloy to overcome the charge transfer limitation. And also, we don't have the imperfections that I mentioned in crystalline alloys. So the amorphous structure provides a more homogeneous structure in addition to excellent mechanical and chemical resistance, and it exhibits also a high thermal and electrical conductivity. So there have been several solutions proposed by the investigators around the world, but almost all the introduced thermal conductive alloys and materials so far had crystalline microstructure. So the crystalline atomic structure consists of several imperfections, as I mentioned, including grain boundaries, elemental segregations, and dislocations, which all of them somehow are preventing the charge transfer in the material. So the proposed technology is to taking advantage of the amorphous structure, like we have a uniform disordered structure of copper-silver binary alloy, in which we don't have these common imperfections in crystalline alloys, so we can decrease the dimensions of the interconnect as low as possible. So we will have this advantage for this technology. So this copper-silver amorphous interconnect can be produced in scalable dimensions, and it's very cost effective. And the technology has a great potential for the mass production, as I mentioned, to be used in electronic devices. So one way for us is partnership through licensing the patents to a manufacturer in electronic industries such as Intel, IBM, semiconductor industry who are dealing with this problem. The other one, a future insight that we were thinking about is investment for starting a startup and production of this technology at larger scale by our own and then sell it to these customers essentially. So for this stage, additional funds are required, such as Small Business Initiative Research, which is SBIR from NSF. It goes up to 2 millions, and it gives us the opportunity to start a startup and then like make them by our own. And also we need industrial partnership and collaboration for obtaining these kind of funds, which we are still in the process of considering which collaborators are willing to partner with us. So we are in the middle of like this stage now.